Bismillahirrahmanirrahim. Today we are going to study rapid thermal processing. Well, in the simplest of the definitions, rapid thermal processing is a semiconductor manufacturing process in which we heat up silicon wafers for a short amount of time. We heat them up, for example, up to 1000 degrees C or even up to higher temperatures than that for just a few seconds. Now, the only care that must be taken in this process is that when you cool down these wafers, the annealed wafers, you have to cool them down slowly. Otherwise, there is a chance of wafer breakage, of breaking the wafers, of breaking the semiconductor samples due to thermal shock. And actually, in my previous lab, this actually has happened that sometimes the students would anneal the samples and then they would ramp down the temperature in a faster way. They would cool them down rapidly, and during this process they would break the samples. So this is the only care that must be taken, that during the cooling process it must occur in a slow manner. And how do you achieve the rapid thermal processing? We achieve the rapid thermal processing either by high intensity lamps via radiation, or by using lasers, or by using electron beams. The applications of rapid thermal processing include activation of the dopants, thermal oxidation, metal reflow, and chemical vapor deposition. The rapid thermal processing categories include rapid thermal anneal, which you perform after ion implantation, or rapid thermal annealing is also performed for activation of the contacts on semiconductors. Rapid thermal oxidation, in which oxidation is performed at high temperature for a short amount of time. Similarly, nitridation, rapid thermal diffusion, and rapid thermal chemical vapor deposition. In chemical vapor deposition, actually we deposit thin films on top of substrates where the chemical reactions actually occur at the surface of your substrates, and due to that reaction, thin films are deposited on top of semiconductor substrates. We can classify rapid thermal processing into three processes: adiabatic processes, thermal flux processes, and isothermal processes. In adiabatic process, we have a beam of lasers, a wide beam of laser, which actually scans a silicon surface, and the transfer of energy actually occurs close to the surface of the substrate. It does not propagate longer or deeper into the substrate. So the purpose is actually to anneal your sample close to the surface. In adiabatic process, we have fast pulses of light, less than microseconds, a broad beam, as you can see over here. Here is XMR laser line beam, which is a broad beam, and it heats only the front surface of your wafer. Now, the disadvantage of this process is that it's difficult to control the temperature in your adiabatic process, and also there are large vertical temperature gradients. By temperature gradient, we mean that the temperature is high close to the surface, but it's the temperature difference between the surface and the substrate is higher. A large difference of temperature between the surface and between the substrate. The second kind of process is thermal flux rapid thermal processing. In thermal flux rapid thermal processing, we have a narrow beam of laser or a narrow beam of electron, and it scans the entire surface in a raster manner. So if you have this narrow beam and you actually scan this entire surface line by line, and at the end of the process you actually scan the entire surface and anneal it. The third kind of process is called isothermal rapid thermal process. In isothermal rapid thermal processing, we have a beam of radiation to heat the wafer for longer amount of times. Now, how do you achieve these radiations? We achieve these radiations by using tungsten halogen lamps. and there are minimal temperature gradients. Now here is an example of rapid thermal processing by using thermal radiation. It's called a Myla 3000 rapid thermal annealing furnace, and I personally have used this furnace for annealing of samples. The only limitation is that we can use this furnace for annealing of only small samples. Like you can see over here, we place our sample in this quartz tube that you can see over here, and at max you can insert like 1 inch by 1 inch sample into this quartz cube. Personally, I was dealing with 1 centimeter by 1 centimeter samples, so I would place approximately 4 samples inside this quartz tube. And once you place samples into this quartz tube, you move this, close the chambers and close the screws on this chamber, and after that here is a window in which you can program the window for heating up. Like for example, you start from room temperature and you want to anneal the sample at 1000 degrees C. So first you have to ramp up temperature from room temperature to 1000 degrees C, and then you keep your sample at 1000 degrees C for a particular amount of time, and after that time is called dwell time. And after the dwell time, you want to cool down the temperature of your chamber, but the cooling is actually performed in a slow manner. You cool down your samples slowly to avoid breakage of your samples, to avoid damage to your samples. In rapid thermal annealing, for example, consider the process of ion implantation. So as we all know that ion implantation actually introduces damage into the crystal lattice. We have high energy ions hitting the lattice sites, hitting the atoms on their lattice sites and dislodging them from their lattice site. And we have a lot of dopant atoms inside this crystal lattice. So then after, what the annealing does is it provides thermal energy to all the dopant atoms, and these dopant atoms, they would move around inside the crystal lattice, find suitable spots, and then find substitutional lattice sites and settle down on those substitutional lattice sites and become activated to donate an electron or to accept a hole inside the crystal lattice. Now, as already told, this heating could be achieved either by using a lamp, via optical radiation, or by using a hot plate via conduction heating. And there is another kind of heating, it's called convection. We are going to talk about that in the upcoming slides. The advantages of rapid thermal processing include single wafer processing, which produces the best uniformity, especially for large size wafers. So you actually anneal the wafers one by one in rapid thermal processing. And there is minimal redistribution of atoms, of dopants. So when you provide heat to atoms inside a crystal lattice, you basically have two parameters. One is the diffusion coefficient of those atoms, or the lattice sites, the lattice atoms. And the second one is the amount of time that you heat up your wafer. And the square root of the product of the diffusion coefficient and time is called the diffusion length, or the length inside the crystal up to which the atoms are going to travel. The atoms are going to travel for a particular length, and that length is called diffusion length. And diffusion length is equal to the square root of the diffusion coefficient times the time of the rapid thermal process. So as we already know that rapid thermal processing is performed at high temperatures, which means that the diffusion coefficient would be higher. But we also know that we perform rapid thermal processing for a short amount of time. So overall, the product of these two would be small, and then the square root of the product becomes small, which means that the diffusion length of the atoms during the rapid thermal process is small, which also implies that there is minimal redistribution of the dopant atoms inside the crystal lattice. So your atoms do not diffuse a lot into the substrate during rapid thermal Rapid thermal process also has its disadvantages. For example, absolute temperatures are almost never known. Why do we say that we cannot measure the absolute temperatures? Because first we ramp up the temperature, so the temperature is not stable, and then we anneal our wafers for a short amount of time. So we do not provide enough time to our wafer so that the temperature becomes stabilized, and then we start ramping down the temperature. So at any point during this process we don't let our temperature stabilize. So that's why we say that absolute temperatures are almost never known. We cannot measure absolute temperatures. And because of that, the non-thermal equilibrium conditions make modeling and the prediction difficult, because the temperature is not stable, so it's difficult to model and predict this process. There are different heat flow mechanisms of rapid thermal processing. One is conduction, the second one is convection, and the third one is radiation. So these are the mechanisms due to which we can achieve rapid thermal processing, or we can achieve heat flow for rapid thermal processing. So let us discuss them one by one. In conduction, there are two solids which are in contact for rapid thermal processing, or for heat flow from one material to another material. For example, here we have a hot plate where we can increase the temperature up to I think like 1200 degrees C, and then here is our semiconductor wafer, a silicon wafer. We place the silicon wafer on the hot plate, and because of conduction, the heat flows from the hot plate to the semiconductor wafer. How does it flow? Because we have solids, so the heating process actually provides thermal energy to the atoms. These atoms start vibrating and transfer energy from the hot plate to the semiconductor wafer. Now here is a formula for heat flow per unit area in a solid, which is equal to KFT, where KFT is called thermal conductivity, and it's measured in watts per centimeter Kelvin. It's an important parameter for heat flow in semiconductors, for heat flow in silicon, for heat flow in gallium nitride, for heat flow in aluminum nitride. So for high power devices especially, we want KFT to have a higher value, and then materials like gallium nitride and aluminum nitride have high thermal conductivity as compared to silicon. So KFT, which is thermal conductivity in watts per centimeter Kelvin, times delta T, which is the change in temperature, divided by X, which is the thickness measured between the two temperatures. And the unit of heat flow per unit area is watt per centimeter square. The second mechanism for heat flow in rapid thermal processing is convection. In convection, the two bodies are not actually in direct contact with each other. The flow of heat actually is performed between two bodies through an intermediate medium, for example a gas. So assume this is our wafer, or silicon wafer, and then we let gas enter into this environment, and the gas actually passes through a heater. So when it passes through a heater, the gas molecules are also heated up, and then these gas molecules actually flow inside this chamber, and these molecules also land on the wafer and transfer their thermal energy to the wafer as well. Now the heat flow per unit area for convection is represented by H, which is the effective heat transfer coefficient in watts per centimeter square Kelvin, times the temperature of the wafer minus the temperature of the gas away from the wafer. Here is an example on convection. So assume a constant power delivery. What is the initial temperature rise rate for a 700 micrometer thick silicon wafer? The thickness of the silicon wafer is given. Generally, the silicon wafers are in the range of 300 to like 700 micrometers thick. In a furnace heated from an initial temperature of 30 degrees C to a final temperature of 1000 degrees C with an effective heat transfer coefficient of 2 10 to the power minus 4 watt per centimeter square degree C. It's given in degree C over here. So the temperatures are given in degree C, and the effective heat transfer coefficient is also given in degree C. So now the heat flow, we have to calculate the initial temperature rise. So as I already told you, the annealing is performed at 1000 degrees C, but first we have to increase the temperature from room temperature, which we over here we assumed is 30 degrees C, to 1000 degrees C. So that is going to take a certain amount of time, and it will have a specific rate. So the difference in these two temperatures divided by the time taken to achieve this temperature of 1000 degrees C would be the rise rate of temperature. But first we need to calculate the heat flow per unit area. We have a formula for that from the previous slide, which is equal to the effective heat transfer coefficient times the temperature of the wafer minus the temperature of the gas molecules. So the heat flow per unit area comes out to be 0.19 watt per centimeter square. Now here is a formula for the rate of rise of temperature. You got to remember this formula, which is equal to the heat flow per unit area in watt per centimeter square divided by the specific heat coefficient of silicon, which is 0.75, times the density of silicon, which is 2.33. These are material parameters, times the thickness of the silicon wafer, which is 700 micrometers, and you have to convert it to centimeters. So the rate of rise of temperature is 1.7 degrees C per second. With this rate, you increase the temperature from 30 degrees C to 1000 degrees C. And if you divide, the difference of these two temperatures is 970 degrees C. If you divide 970 divided by the rate of rise, you get the time taken to increase the temperature from 30 degrees C to 1000 degree C. Alright, moving on to the next slide. Okay. The third heat flow mechanism is radiation. So we already discussed conduction and we discussed convection. The third heat flow mechanism is radiation. During convection, as we already discussed, that the heat flow is performed through an intermediate medium, through gas molecules. But the amount of power that can be delivered through gas molecules is limited. So a more effective way of performing rapid thermal processing is by using radiation as a primary source of heat exchange. In radiation, we have lamps. These lamps are mostly tungsten halogen lamps, represented by the yellow dots over here. We perform the rapid thermal processing in a closed chamber, and we place our wafer inside this chamber, and then we have a pyrometer to measure the temperature with respect to time as well. These are different examples of rapid thermal processing achieved via radiation through different kind of lamps. Mostly these are tungsten halogen lamps. I already discussed one of the examples of radiation in one of the previous slides. Let me go back to that slide. I told you about this Myla 3000 rapid thermal annealer. Inside this chamber we have lamps surrounding the quartz tube, but the only limitation of this is that the sample size is the maximum sample size for annealing through Myla 3000 is approximately 1 inch by 1 inch. For bigger wafers we use systems like these shown over here. Moving on to the next slide. Here is the formula for radiation. So m lambda of T is actually the spectral radiance excitancy, which is the radiated power per unit area per unit wavelength, is equal to emissivity times C1 divided by lambda to the power of 5 times exponential of C2 divided by lambda T minus 1, where C1 and C2 are given over here. and E of lambda is the wavelength dependent emissivity. But if we consider, if we assume that E of lambda is independent of wavelength, then M of T is actually comes out to be heat flow per unit area. M lambda of T is the radiated power, watt per centimeter square per wavelength, in nanometers or in micrometers. But if this is wavelength independent, then its unit becomes watt per centimeter square, or then it's equivalent to the heat flow per unit area, equal to emissivity times the Boltzmann constant times temperature to the power of 4. And we already know the value of Boltzmann's constant. In this slide, I have given a comparison of the formulas of different heat flow mechanisms. The first one is conduction, and the heat flow per unit area in conduction is linearly proportional to the change in temperature. Similarly, in convection, once again, the heat flow per unit area is linearly proportional to the change in temperature. But you might notice that in radiation, the heat flow per unit area, when the emissivity is independent of wavelength, is proportional to temperature to the power of 4. So comparing these processing, you can say, or you can conclude that conduction and convection are more effective at lower temperature, but radiation is more effective at higher temperature because of the temperature to the power of 4 dependence of heat flow per unit area in the radiation process. Now, here is actually a numerical from your book, Microelectronic Fabrication. A rapid thermal processing system is used to heat a 200 millimeter diameter silicon wafer to 950 degrees C. Temperature is given, the diameter of the silicon wafer is given. If the effective emissivity of the wafer is 0.7, use this equation to calculate the amount of power necessary to maintain this temperature. So we have to use the formula given in the previous slide, which is heat flow per unit area is equal to emissivity. Now in this example, emissivity is given times the Boltzmann's constant. We already know the value of Boltzmann's constant, times the temperature to the power of 4. And we know the temperature as well in this example. So first, let us solve part A in this example. But over here in formula, Q dot of T actually represents heat flow per unit area in watt per centimeter square. Or you can replace it with P divided by A. And in example, we are asked to calculate the amount of power, not the heat flow per unit area or the power per unit area. So it's simple. Heat flow per unit area is equal to emissivity times the Boltzmann constant times the temperature to the power of 4. First calculate the area. The diameter is 200 millimeter. So the radius becomes 100 millimeter or 10 centimeter. Area is equal to pi into 10 centimeter square. So this becomes 100 pi. Over here you see, I think they have calculated 200 pi, but it actually becomes 100 pi. 10 square into pi, 100 pi. So then power is equal to area. Area is given over here times emissivity is given in the example 0.7 times temperature to the power of 4. Convert temperature from 950 degrees C to Kelvin, which comes out to be 1223 Kelvin to the power of 4. So the power necessary for this heat flow mechanism via radiation is 5.6 kilowatts. So once again, let me try to go back and let us try to understand where does this power comes from. So as I already told you that the radiation process is actually achieved via lamps, mostly tungsten halogen lamps, and you have to supply power, current and voltage to these lamps, right? And you have to anneal your samples for a particular amount of time. So this is actually the power consumed during that annealing process for that particular amount of time. Okay, now let us go to part B of this example. If one wants to ramp the temperature at 100 degrees C per second, what additional amount of power is required? You can assume that the wafer is 700 micrometer thick, and there you can use the room temperature specific heat and mass density for silicon given in appendix 2. Okay, we talked about annealing and the power consumed during that. Okay, I guess Khizar, you have a question? Go ahead. Khizar, you raised your hand. I assume either it happened mistakenly or you got a question. Do you have a question?
No sir, गलती से हाथ लग गया था मेरा.
Okay, no problem. Okay, so during part A, we assume that we annealed the sample at 950 degrees C for a particular amount of time, and we calculated the power consumed during that particular amount of time, and that time is called the dwell time. Now, we also know that initially we have to ramp up the temperature from room temperature to 950 degrees C. So in the second part, we are asked to calculate that amount of power, the power required to ramp up temperature from room temperature to 950 degrees C for the tungsten halogen lamps or whatever other kind of lamps that we are going to use. And in one of the previous slides, and the temperature rise rate is given 100 degrees C per second. In one of the previous slides, we already applied this formula, dT divided by the derivative of temperature with respect to time is equal to heat flow per unit area, which we calculate in part A, divided by specific heat coefficient, which is a material parameter, we know that, times the density, that also is a material parameter, we know that, times thickness is 700 micrometers or 0.07 centimeters in that example. And power we calculated in the first part of the example. Area we also calculated. This is power divided by A. So going to the second part of the example once again. So rearrange the equation given in the one of the previous slides that I showed you. Dt divided by dt, the derivative of temperature with respect to time is equal to. So here is, okay, let's go back to this slide. Here is the formula. Rearrange it for heat flow per unit area, and this is equal to P divided by A. But then P divided by A, the A or the area goes to a denominator, and area times thickness is equal to volume. So replace it with P divided by specific heat times density times volume, and then rearrange it for power. Okay, so power is equal to volume times specific heat times the temperature rise rate times density. Volume is 100 pi area times the thickness, which is 0.7 centimeter for silicon, times specific heat coefficient is 0.7 once again for silicon, or 0.75 that we assumed in one of the previous slides. The rise rate given in the example is 100 degrees C per second, and the density of silicon is 2.33 grams per centimeter cube. So the additional power required is 7.17 kilowatts. This is the power required to ramp up temperature from room temperature to 950 degrees C. And this is the power required for the dwell time, for the amount of time that we perform the annealing. Okay, now the question is, how do you measure the temperature during this process? Generally, you measure the temperature via a thermometer, and in a thermometer, you actually make physical contacts to the surface on which you want to measure the temperature. But for this process, for the rapid thermal annealing, you don't measure the temperature via a thermometer. You don't make physical contacts to the heated surface. we measure the temperature using a pyrometer, and pyrometer is used for a lot of other systems. For example, for measuring the temperature of for molecular beam epitaxy, which is a growth process. So for the temperature measurement, we have a heated source, and we want to remotely measure the temperature of this heated source. This heated source is going to radiate light of different wavelengths, and the pyrometer actually has a lamp. It absorbs those radiations, and based on its mechanism, it actually measures that temperature. But the basic point is pyrometer is actually a device used for temperature measurements, and it measures the temperature of a surface remotely. The same information that I already told you in the previous slide. And pyrometry is sometimes known as radiometry as well. So it was kind of a short lecture. That concludes the lecture. As I already told you that I'm recording the lecture, so I'm going to save the recording.